Alright folks, so welcome to our next lecture in special relativity prerequisites. Today we're going to be discussing about Green's theorem, and hopefully I can give you a sense of why Green's theorem works, how it relates to the concept of line integrals and work in scalar and vector fields, and we're going to use this concept hopefully in special relativity. It is one of the prerequisites for special relativity because it is one of the largest theorems in multivariable calculus. Okay, so first and foremost, before we get started with any concepts or problems or ideas, I want to make sure that this is live streaming and being broadcast on both Barry Science Lab, the Facebook, and Barry Science Lab, the YouTube site. So let me go ahead and turn that on. Okay, so hopefully that just got turned on. So if you're tuning in from Facebook, welcome to our second lecture in special relativity prerequisites. Remember that these are not in order, and you can watch them in any order that you choose to. For those watching on YouTube, right now we're going to go ahead and verify that this is live to the audience. And indeed it is. Okay, indeed it is. So let's grab that keyboard here, and I'm just gonna shift everything the way it should be. Okay, so let's check the audio. Yeah, so audio should be pretty good on that end. But now what we're gonna go ahead and start doing is let's just start with the problems, right? Let's start introducing the concept of Green's theorem. Why is it so important, and why should I care about it? Before we get started, I'm going to mention to the live audience, if you have any questions or comments, please let us know in the chat below. So, let's mention that to the live audience. If you have any questions about math or science, please let us know. Okay, with that out of the way, we're ready to go ahead and get started with Green's theorem. Before we do so, however, I think it would be wise to put a thumbnail on this video so that people know what we're doing today. In the meantime, however, let me progress to the Green Theorem homepage. So you can see here I've set up a very indicative profile picture of what Green Theorem might be about. So in the meantime, I want you to comment down below what do you think Green Theorem might be about, right? How might it relate to, curl, divergence, maybe circulation, or maybe even air conditioners, who knows. Go ahead and comment down below what do you think Green's theorem is all about, and we're gonna go ahead and tackle it very soon. Okay, so in the meantime, in the intervening time, I will put a thumbnail on our video right here. While I'm doing that, I encourage the audience to go ahead and post any comments or questions they have on math and science down below. I'll be happy to answer them. Okay, let's take the live problem solving stream. So today we're doing Green's theorem. Let me know also if you're hearing me well. Otherwise, I may have to change my microphone. Okay, so let's put the link down there. This will inevitably help us. No, it's not made for kids. And let's put an adequate thumbnail right there. An adequate thumbnail. Boom. And that thumbnail will be on our way. So let's just post that thumbnail where it belongs. where it belongs. Okay, in the meantime, if I see any questions from the audience, I'll be happy to answer them, whether they be about math, science, astronomy, or otherwise. So let's go ahead, go to the live stream. Let's check the audio right there. Go to the live stream. Let's check the audio right there. Okay, so audio, video, everything seems good, and we're operational, and we're ready to go ahead and tackle Green's Theorem. Now, before I go ahead and start talking about Green's Theorem, I want to preface it by saying that you should already know the concept of line integrals. Line integrals. Right now, what are line integrals? When you think about line integrals, the first thing that should pop in your mind is the concept of work, right? So how can I change this? Let me just switch accounts. So what is work? Well, let's take a physics book to aptly demonstrate the concept of work, right? So when I'm exerting a force on the book over a certain distance, I'm really exerting work on the book, right? I'm doing positive work on the book, and I know my work is positive because the kinetic energy, aka the speed of the book, increases. Now, the gravitational field in which this book exists is a conservative vector field, meaning it doesn't matter what path I take to exert work on my book. The only thing that matters is the start and ending point of my book, right? Of where I take my book. I don't know why it's showing this kind of YouTube studio thing, but we're gonna proceed ahead nonetheless. So now that you know what the concept of work is, or at least have a review of it, what does the idea of line integrals contribute to work? Well, let me tell you. The concept of line integrals is quite simple. It's basically projecting a 2D path, a 2D curve on the XY plane, and finding the volume, the area or the volume that it encloses in 3D. So let me show you what I mean, rather than bumbling around here. YouTube makes it incredibly difficult to actually put a thumbnail in place for a video, which is quite unfortunate. But let's go ahead and save that title right there. And in the meantime, we're gonna transition back to scene 3, and I encourage the viewers to go ahead and understand, or at least try to guess in the comments down below, what Green's Theorem is all about. What's the moral of Green's Theorem, right? What does it teach us about the line integral, or about work in general? Who knows, right? So I'm just gonna go ahead and change in the meantime our thumbnail, so that we actually have viewers who know what we're talking about. Hopefully that won't take too long, but we're gonna get that done in the intervening time. Now while that's happening, I want the viewers to go ahead and understand the connection between line integrals and work. As a matter of fact, we don't use line integrals for just work. They're also used for, as I said, finding the area of a curtain in 3D space. Right, and as a matter of fact, I'll show you what I mean by that in a few seconds. As long as we can get that up here, we'll be done and ready to go. Let's see if YouTube wants to cooperate with us today. And boom. It's been sent. Let's see if our message has arrived to the audience. Now we're receiving too many comments at this point, so I'm gonna have to enable the moderator, so he'll be taking your questions, and any questions that are important will be directed to me, and I'll do my best to try and answer them. Okay, so let's see if this screenshot can be put up here. Okay, so in the intervening time, in retrospect, I should have prepared for this moment if YouTube inevitably fails. But in the meantime, let's go ahead and go back to our Jamboard, which is where we're going to be doing our math. So let's see. We have our screenshot right here for Green Theorem. We have too many people watching. It might overload our servers at this point. So if you're having any interruptions on your end, I encourage you to go ahead and reload the site. Okay, and we have officially uploaded the thumbnail. The audio is perfect, the video is perfect. We're ready to go ahead and start tackling Green's Theorem, folks. How exciting is that? How exciting is that now? Now that we're ready to start Green's Theorem, I wanna take it slow and steady, because this is really the crux of multivariable calculus. The beginning of special relativity really starts here. We're gonna start unraveling the connections later on, but this is where our journey starts, with Green's Theorem. So, what is Green's Theorem all about? Well, to find out, today we're gonna be taking a look at, first and foremost, the line integral. The line integral, okay? Let's take a look at what the line integral is all about. So, the line integral begins with a very simple idea. Right? Imagine you have a kind of wind, for example, airflow. Think about airflow. Air is flowing through space, and there's an airplane, right? So let's go ahead and search that up. Airplane and airflow. Okay, let's go ahead and take a picture of that. So what you'll see right now is the concept of airflow, right? So hopefully you're seeing what I'm seeing right now, and that is essentially hopefully you're seeing the animation itself as well. So what we have right here is particles of air being compressed and decompressed around the wings of an airplane, right? That's hopefully what you're seeing right here right now. But how can we understand this in terms of work? Obviously, the wind is exerting some kind of work on the airplane's wing. But how can we understand the amount of work exerted by the vector fields, which describes the wind particles, on the actual wing of the airplane? How can we understand that mathematically? Well, that's why we have the concept of work and line integral. So let's take a look at the line integral. The line integral basically tells us that, let's go back to our Jamboard right here. Okay, so the line integral, what does it tell us? Let's actually go to the next slide for our Facebook audience, who apparently doesn't see what we're seeing. So the line integral, quite simply, tells us we have a field, right? A vector field. And this vector field is flowing in a certain direction. So for example, this is our vector fields. In this case, it's flowing in this direction, and you know, this vector field can be 2-dimensional, 3-dimensional, whatever, n dimensions, right? When we're talking about space and time, we're really talking about 4 dimensions, 4D, 3 for space, and 1 for time, right? 4 dimensions. But here we're sticking straight and simple, and that's in 2 dimensions, right? So our line integral is gonna be, first of all, it's gonna have a field, a vector field, and that vector field, let me write it down. Let's call that vector field f, right? Hopefully you're seeing what I just wrote down there. And that vector field is gonna be described in terms of functions, right? Those functions being, of course, being p and q. P representing the x component, and q representing the y component. That's just convention. Okay, so maybe I can write it as such: p of x comma y and q of x comma y. Okay, so that's really how we tend to express a vector field, right? A vector field, a 2-dimensional vector field, is going to have an x component and a y component, right? And an x component is, of course, going to be a function, a kind of scalar function that accepts 2 inputs and spits 1 back out, and same for the y component. Okay, and that is going to describe the vector fields that we're concerned with. But there's a curve, there's a path happening in our field. That's why we're interested in this line integral in the first place. So we have our fields, and we have a kind of function, a vector, to describe our fields. But we also have a path, and let me draw that path out for you. Here we have our path. How can I draw it out? So here in blue, you see our path, and it's going from, I guess, from left to right. You can almost describe it as such. Now, what's interesting about our path is there's a particle moving on it, right? If I zoom in, you can see there's this particle A, and it's moving along this path. Now, the only reason it's moving is because there's an external force. That external force is due to the vector field exerting an external force on our particle A, such that our particle A moves on a certain curve, right? In a certain curvilinear path. Now, in forcing our particle to move, the field exerts work on our particle, and our goal, our desire, is to find the work exerted by the field, by the vector field on our particle. Okay, so with that out of the way, let's go ahead and take a look at the formal definition of the line integral. And I'm gonna go to the next slide for our Facebook audience. Let's see how many Facebook folks we have. A fair amount being 11. So, line integrals, math. How do we connect those two concepts? Well, let's say you've got a ball. I've got a ball right here. Hopefully everyone can see it. So here's my ball. So there's my ball right there, right? Now, I want to find the mass of my ball. My ball may or may not have uniform density. It certainly has volume, certainly has area, but my main goal is to find the volume, the mass of my ball. How do I do that mathematically? How do I calculate the volume of, I keep saying volume, the mass of my ball? How do I do that? Well, the answer is, quite surprisingly, I guess, line integrals, right? The line integrals are going to be the key to helping us find the mass of this ball, of this non-uniform density ball. Okay, so let's go ahead and do that. The line integral tells us quite simply that we have a function f, right? So we have a function f of xy. Okay, whoops, that's not a very good parentheses. Now, what is this function telling us? Well, this function f of xy is going to give us the mass per unit length of the string, right? So for example, if my string looks something like, let's see, let me find an image of a rope. Let's get an image of a rope right here. Not a straight rope, but a curvy rope. Okay, so let's say we have something along the lines of this. Obviously I can't get a great picture, but you get the point, right? I have a rope, and let's see, something like this. Now the fact of the matter is here's my rope. If it's gonna even arrive here, that is. Whatever, I can just draw it out for you. So here is a rope. Imagine we have a rope right there. So right, we have something like that, and that's a rope, right? And an infinitesimally small slice of our rope, a very, very small slice of our rope, is going to have a mass given by this function f of x comma y, right? So for example, at this point x comma y, our rope is going to have a mass given by this function f of x comma y, right? So hopefully that sets the tone for what we're going to do now. Now that we have a function that gives us the mass per unit length of our rope, we need one more step. And what is that step? Well, we need to integrate the mass per unit length of our rope over the entire rope, right? And how do we do that, right? That becomes the key question. Well, here's how. Sorry, we seem to have a disruption. No. Okay. Well, we simply have to find the arc length of our rope at this point. So how do we find the arc length of a curve? Well, let's say this is our curve of interest right here. Let's zoom in. Now we can take this curve and kind of break it down into a line, right? If we zoom in sufficiently enough, if we zoom in to a sufficiently large scale, this curve is going to start looking like a line, right? There's our curvy linear line, if you will, right? And that line is perhaps a small change. Let's call that change ds. And of course that small change by the Pythagorean theorem can be broken down into components, dy and dx, right? So let me show that out for you. So this right here is going to be our dy, and this right here is going to be our dx. Okay, so we've effectively broken down our infinitesimally small, tiny change in our curve into its component vectors dx, dy, right? So now we can go ahead and write the following equation, which I'll go ahead and write in yellow. So we can write f of xy, right? Hopefully you can see what I'm writing. F of xy, and we're integrating it along the curve, so ds, right? And let's call our curve c. For the moment being, let's call our curve c. Okay, so that's essentially the line integral, the definition of the line integral. But now I'm going to expand it a tad bit, and I'm going to ask you, audience, to go ahead and suggest to me how I might go ahead and expand the line integral. Go ahead and good luck. Okay, so hopefully that was sufficient time to go ahead and consider how we might expand this equation for the line integral. Now I'm going to go ahead and actually do it. So here we go. Let's go on to the next slide and duplicate this. So the Facebook audience will have to follow along as well. So here we are, back with the line integral, but now hopefully you have the diagram in your mind and you don't need this anymore. Now what we're going to do is expand this, right? We already know that whoops, wrong slide. We already know that ds is going to be the square root of dx squared plus dy squared, right? That's just Pythagorean theorem. Hopefully you're accustomed to that. But now we need something else, right? All we need to do is go back to our line integral, which is what? A line integral was the integral over the curve of our function f of x, y times this this kind of square root of dx squared dy squared, right? So times this radicand. Okay, but recall, usually when we have these kinds of curves, we want to parameterize them. Parameterizing these curves allow us to do whole kinds of maneuvers, so we can actually expand this further, right? This is not the end of the ball game, right? So as a matter of fact, let me go ahead and take a screenshot of this, and we're going to make it this smaller. So here we are. Here we are. Okay, now that I have that equation, what I'm going to do is express everything in terms of a single parameter t. Okay, so let's go ahead and do that in red. So I'll have the line integral over the curve of f of x of t, comma, y of t. Right, so far so good. Root what? Well, we're gonna have again dx squared plus dy squared, but here's what I can do. Here's what I can do is pull up a little magic trick, right? Multiplying by dt over dt, because t is of course our parameter, and we need to keep that in mind, that we need to express everything in terms of our original parameters. So let's go ahead to the next slide so we can do that. For the Facebook audience as well. There we go. Is this the duplicate slide? Yes. So let's go ahead and erase all of this. Can I erase this? Yes. Or at least I hope so. Okay. So now how can we progress from this? Well, I just said we're going to multiply that radicand by by just dt over dt, which is effectively just 1, right? So what I'm going to do is, let me just rewrite that radicand for a second. So I'll have the integrand over the curve, right, of f of x of t, comma, whoops, comma, y of t, comma, y of t, right? So far so good. Times what? Well, times our radicand, remember, but this time we're multiplying it by dt over dt. So hopefully you recall that. And then we're going to multiply by our radicand, which is root dx squared plus root dy squared. Okay, so hopefully so far that's so good. Let's as the audience, if they're following along, Okay, so now what we're going to do is, now that we have that dt over dt, we're going to try to bring that into our radicand. Okay, let's see if I can do this, because I haven't done this in quite some time. So f of x of t, and I'm going to zoom all the way in, comma y of t, and after we bring that dt over dt inside, what I should get is something along these lines, right? So I'm going to get dx squared. So let's keep one of the dt's outside, okay, just to be fashionable, just to be safe. So what I'll end up with is dx squared over dt squared plus dy squared over dt squared, all multiplied by dt. And there you go, folks. That is quite precisely the definition of the line integral, right? And maybe I'd be willing to go just a tad bit further, just to humor myself, I would say. Let's see if we can take that extra leap. And let me erase this. Okay, so now what I'm going to do is say that x of t and y of t is going to come in the form of some kind of vector valued function, r of t. So let's see if the YouTube is following along. Yes. So let r of t equal the following: x of t, y of t. So it's basically a vector valued position function. That's it. Nothing fancy, nothing crazy. So now now that I've defined r of t as such, what I'm going to do is just simplify that, right? So I'll have the integral along the curve, the line integral along that curve of f of r of t, r being a position vector, and then I'll just have root, what is that, dx squared dt squared. Well, another way I can possibly write that is using the divergence formula, right? Dx dt squared. That's an interesting dilemma. How do you handle that radicand? Well, let me ask the audience. How should I handle that radicand? Handle the radicand. So if anyone out there can go ahead and give a guess as to how we're gonna simplify that radical, go ahead and give it a try, and let us know in the comments below. So I'll give you a few seconds to go ahead and answer my question as I go ahead and scroll through the comments and questions. Okay, so how can we handle that? Well, one thing I had in mind was simply as follows. I have dx dt and dy dt, right? And both of those are simply what? Simply components of my vector valued position function, right? So I can actually just choose to leave them be, or I can simplify them, but I'll just leave them as b, dx dt whole squared plus dy dt whole squared. That's really the formula that's going to allow you to compute all of this mess in the end. But the moral of the story here was not to give you a full-blown explanation of the line integral, but really to give you a sense of how you can get the line integral from the concept of mass and from the concept of work, right? So, what should you take away from this? What's the moral of the story? Well, I'd say the moral of the story is quite simple, and it's as follows. The line integral, the line integral is, for me at least, I've used it in 2 applications thus far. Okay, 2 applications thus far, and I'm sure you can guess what they are, given the fact that we've just covered one of them. First and foremost is mass, right? handling mass, finding the mass of irregular objects, curvilinear objects, right? That's one. Number two is, of course, finding the work done by a vector field on a curve or a path. Okay, so hopefully that gives you a broader sense of what we mean when we talk about line integral. But today's all about Green's theorem. That was just the foundation, and hopefully you've come to understand that. Before we go ahead and begin the Green's theorem, I want to give a quick debrief. What did we just learn from doing the line integral for so long? Well, I myself, from lecturing right now, have learned the following. First and foremost, the line integral is very versatile, right? One can use it for finding mass. So, for example, if I want to find the mass of this sphere, what I'd use is the line integral, right? Why would I use the line integral? Well, the line integral allows me to find mass not because no other function can, but because, for example, if you have an object with non-uniform density, the line integral can help, especially if that non-uniform density can be expressed as in terms of a function, right? So, for example, let me give you a real life example. Let's say I'd like to find the mass of this stapler. How would I find the mass of this? Well, I can take an infinitesimally small chunk of this stapler, and I can use a function f of xy that defines the mass of that infinitesimally small chunk, and I can take that function f of xy and take its dot product with the small change in surface area of this stapler, right? So essentially what I'm doing is taking the dot product of, number one, that infinitesimally small mass and the function that defines it, and number two, the kind of area, the small change in position on the surface of the stapler, right? Which you can denote with a vector value position function. Okay, so hopefully that gives you a sense of the line integral in terms of mass. But of course we can also examine it from the perspective of work, right? So for example, how much work does the wind exert on this ball and make it go on a certain curvilinear path? So that right there is the concept of the line integral. Now we're going to move on to the idea of Green's theorem, and hopefully that rant on line integral will give you a much deeper perspective on Green's theorem. So let's go ahead and take a look. In the meantime, however, I will be pausing for a 20-second break, during which I encourage you to look over and review what we've just accomplished. Okay, so now let's go ahead and move on to Green's theorem. Green's theorem. Yes, perhaps one of the greatest theorems in multivariable calculus. So, what is Green's theorem? Why is it so important? What does it do? That's what we're about to find out. Green's theorem says this. It says that the line integral, so let me write it down. The Green's theorem says the line integral, the line integral over a specific curve, and that curve must be closed, right? So we'll have the function f defining, some mass or some other scalar quantity dot r, right? R being a unit vector or unit tangent vector, ds, right? That's what we all know and love. That's simply the line integral. That's just the line integral, right? But Green's theorem tells us that line integral is equal to a double integral. And when I'm talking double integral, immediately, your mind should go to 3 dimensions and 2 degrees of freedom, right? So there's our double integral. And we're going to be doing our double integral over some region D. Okay? And here's the kicker, right? It's going to be equal to delta Q, delta X. Sorry, I shouldn't be saying delta, I should be saying partial, minus partial P, partial Y. All of this followed by what? Well, let me show you instead of telling you. Let's show the audience what I mean by that. Well, there you go. That is Green's theorem, right? We have on the right hand side a double integral, and on the left hand side a line integral. And that's just kind of weird, right? If you think about it, how are these two things coming together? Well, it's our mission today to understand that. We've already understood the line integral in quite some depth. We've understood it as exerting some work, as a vector field exerting work on a particle, and we've understood it in terms of mass, right? Finding the mass of a particular object via the line integral. So we've understood the line integral, the left-hand side of the equation. But how in the world is it equal to the right-hand side of the equation? Well, that's what we're here to explore right now. Let's go ahead and duplicate this slide and move on to the next slide in a hope to understand what the Green's theorem is actually talking about. Okay. In the meantime, let's go ahead and check our Facebook audience to see if they have any questions, and that's a definitive no. Okay, so great. Let's erase all of this and understand what's happening. Okay, starting from a clean slate. Well, let's start with a picture, shall we? A picture to help us grasp what's happening. And my picture is going to start in our good old XYZ coordinate plane, Cartesian coordinate plane. Okay, there's our XYZ coordinate plane. Now what's going to happen on this plane is I'm going to have a closed curve, a simple curve. So let me draw that out for you. So let's say I have that kind of SpongeBob looking curve, and that curve is going to be, every point on that curve is going to be associated with some kind of z value, right? It's going to be associated with a scalar function that's going to output a z value. Okay, so here it goes. So for example, okay, so there you go. There's our path, our surface on which that that thing is gonna lie, that surface. And here's what we're talking about. Here's what we're talking about. You can see I'm connecting my 2D path on the xy plane to my surface above it, right? Okay, that right there is Green Theorem in a nutshell. Okay, it tells us quite simply this. It tells us that the line integral of whatever is lying down, whatever path is lying down there in the xy plane, is equal to the double integral of that surface, of that curtain. Alright, so what do I mean? Well, let's grab a picture to illustrate. Okay, so when do we use the double integral, you may ask? Well, the double integral is used when we need to calculate the volume under a surface. And indeed, that's exactly what we're doing here, right? If you imagine this surface here, we're simply calculating the volume under the surface as defined by the curve in the xy plane. That's why we need that double integral, right? Why can't we do it with a single integral? Well, because we have 2 degrees of freedom here, folks. 2 degrees of freedom. Now, we know what the right-hand side of the equation is saying now, right? It's saying that we need to, that double integral right there, right? That double integral is saying what? Let me actually write here. So that double integral tells us the following. Yikes, this isn't the optimal drawing solution. I realize that. But the double integral of partial q partial x minus partial p partial y over the region R, which I should have actually denoted right there. So there's my region R. What is that double integral telling us? Well, it's telling us simply calculate the volume of this curtain, right? You can see this kind of curtain looming under our surface right here. And all this double integral tells us to do is find the volume of that curtain, right? So I'm outlining that curtain right here to make it really explicit for you viewers. But hopefully it should be clear by now that that double integral is simply referring to the volume under that curtain, right? So, I mean, it is quite hard to draw it manually, but hopefully you understand what I'm trying to illustrate. Okay, let's go back to our YouTube audience. No comments there, but go ahead and ask us any questions. Feel free to do so. Now, that's the right-hand side of our Green Theorem. What was the left-hand side? Do you remember? Let's go ahead and write down that left-hand side. The left-hand side was telling us to find the line integral across that curve C, or in this case rather R, right? And now hopefully you're starting to get a sense of why those two are equal. One is telling us to find the volume under basically a curtain in the XYZ plane, and one is telling us to find the work done on a curve, on a particle traveling on a curve by a certain vector field. how do those two have any relationship with each other? One is a volume, one is a work, or rather one is a mass. You can even think of it as a mass. Well, here's what's happening. One interesting route I'm thinking of taking is that obviously density is mass per unit volume, right? Kilograms per cubic meter, right? That's the entire definition of density. We know that the line integral is essentially a formulation of mass, right? This right here is simply mass, right? That's mass, or I can just denote it with the letter M. What about the left-hand side? What is that? I mean, it certainly doesn't look like mass. It looks like some crazy partial derivatives, right? So what's going on that left-hand side, and why is it equal to mass? Well, since that's a tricky question to answer, we're going to pivot. We're going to change our perspective to a different question. But our goal is the same, to understand why the left-hand side is equal to the right-hand side. What we're going to do is take the perspective of work. And that's why I've taken the liberty of taking a look at this vector field. Okay, so hopefully everyone's looking at this vector field right now. Take a moment to examine this vector field. What's happening here? Well, in dark blue, you're seeing a vector field, right? So let me just draw out some of those arrows for you. Here are some of the arrows that are part of this vector field. And like any vector field, this one is defined as follows. It has an x component and it has a y component, right? So let's actually bring this one closer, and this one is fine right where it is. So like any vector field, this one we can express as f of xy, right? And it's going to be defined using two components, one being p, that's our x component, and one being y, that's our, one being q, that's our y component. There you go. Alright, hopefully you see that. Hopefully that's not too small, too shabby. That's f of x comma y. That's our vector fields. Okay. I'm trying to understand this step by step. Number two is our curve. The curve, or the path, taken by a particle. Now that path is shown here in red, and I won't hesitate to do the same. You can see that I'm tracing out that path right here, right now. Right, first, you can see first and foremost that this path is clockwise, right, or counterclockwise rather. So first it goes to the right, then we're going up, we're going left, and finally we proceed to go down. So we have some counterclockwise motion right here, right? So that's another thing to notice. Counterclockwise motion. What else can we notice? Well, let's set some bounds on our domain, right? Because without any bounds, our domain is going to be kind of left for judgment, right? So let's pull this up a little bit, and let's specify exactly what our domain is. Well, let's say our x components start at A and end at B. And let's say our range starts at C. Because this is a function, I can't call it f of a. So I'll just denote it with C, and my upper bound I'll denote it with D. Right? So to restate, what are the bounds on my path? Well, quite simply, they're as follows. It's going to be, well, first of all, I need to give my region a name. Without a name, there's no region really. So first and foremost, let's erase these arrows. And let's give this region a name. Right? So we'll have, we'll denote this region as D, or C, or whatever. Let's go ahead and check if we have any comments from our YouTube viewers. Not really top chat, but live chat. Okay. Well, that's disappointing, but we carry through. Anyway, back to the point. What are the domains on our path? Well, quite simply, I can write them as follows. My path being D, I can say that D is confined to the following. Right? So I'm going to limit my x and y to be as follows. I said that x is going to be between a and b, inclusive. So let's write that down. Hopefully everyone can see that. And with y, let's say that I think I said that y is bounded between C and D. Okay. So there it is right there. Those are my bounds. Okay. Now it's time to find the net work done on our object. Before we tried to tackle it with the perspective of mass, but now let's try to tackle it from the perspective of work, and let's see if we make any further progress. Okay, so how can I go to the next slide? Well, I can just go ahead and hit or tap next. Now let's do the same for our Facebook viewers out there. Okay, so my goal is to find the net work done on this particle. So I'm going to take it step by step. Let's first find the net work done as we progress, seems like my phone itself is frozen. So let's find the net work done as we progress from left to right. So on this path right there that I highlighted. So to find the work done there, what do I have to do? Well, I take the line integral, folks, the line integral. Let's see if I can get anything out of all those line integrals. So my line integral is going to be obviously, well, this one's not closed yet, on the curve or the path C. And I'm going to take the dot product of f dot the unit vector, the unit tangent vector in this case, because we want to see how much the field is going in the direction of our path, ds. Okay, so far so good. And what is our f? Well, we can let's just go general here. Let's say our f can be defined in terms of P and Q, just as we did before. Take a sip of the life-saving water, and we're back in action. So what about our unit tangent vector? Well, notice something here. Notice that our unit tangent vector is simply going to be in the direction of motion, right? There's our unit tangent vector. And just before we compute the actual line integral, does it seem like the field is helping or hurting that line of motion? To me, it seems like it would be helping. Why? Because take a look at the x and y components. The x component is definitely helping. The y component doesn't contribute much, but the x component of those teeny tiny vectors certainly look like they're helping, right? So let me actually zoom in sufficiently, and you'll see that these x components are in the same direction as my path of motion, my direction of motion. So I'm expecting my line integral to come out positive, at the very least. Just a basic sense of intuition. Okay, with that out of the way, let's actually compute the line integral. Alright, how do we compute that line integral? Well, it's going to be quite simple. We know that our unit tangent vector is simply going to be 1, 0. Right? They're all just going to be unit I hats, if you will, unit I hats. So if I do f dot r hat, what am I going to get? Well, if I dot this with p and q, all I'm going to get is p. All I'm going to get is p. So what's the moral of the story? Well, f dot r ds is just going to equal, let's actually erase some of this because I don't have much space. So it's going to equal what? Well, quite simply, we're going to have the integral over our path, over our curve, of just p of x comma y ds. Right? But one thing is that the y is constant here. It's held constant, and it's held constant such that y is just going to be c. Recall that we set bounds just the previous slide, right? So that right there is the work exerted on our particle by this field, and as expected, that work is positive. So that right there is done. Next slide, we're going to compute the work done by the vector fields. By the vector fields on what? On the top path, right? So what do I mean by the top path? Well, I mean this. How did I highlight it previously? I used the color red. So now we're focusing up top, right here. That's our main interest of focus right now. Well, first and foremost, let's write the formula for line integrals. We have as follows: the integral of what? F dot r hat ds, right? And what is r hat? Well, in this case, it's going to be negative 1, comma 0, right? You can just see that the motion, the vectors along the path of motion are going to be in the negative x direction, or negative I hat, if you will. Okay, so we're going to have the same mumbo jumbo, right? F dot r hat is equal to pq, and of course the dot product is commutative. That's why I can just switch these up. So dot negative 1 comma negative 1 0, that's just gonna equal negative p, right? So that means this whole jumble of mess is equal to the line integral along that curve. Let's draw a nice integral of what? Negative p x comma y ds. And of course, once again, we're holding y constant, this time at d. And as you might have expected, the work done this time is negative. Why? Well, you can see that this time the x components are actually going this way. Sorry, let's use that color. So that x components are going that way for the vector fields, but the x components of the path of motion is going in the exact opposite way. So obviously this vector field is impeding the motion of our particle. It's slowing it down. Kinetic energy is negative. Thus kinetic energy can never be negative. Kinetic energy is decreasing. Thus work must be negative. Thus our line integral must be negative. See that path of reasoning, that logic? That's what's really happening right now. Okay, so we just did our first two line integrals. Right, let me write it big and huge for those of you who are interested. Minus p of x comma d ds, and that right there is our work done across the path of interest. Next slide number 11. Now what are we focusing on? Now we're focusing on the left and right paths of motion, right? So let's highlight those. Let's first focus on this one, this bad boy. How do we calculate the work done by the vector fields on that path of motion? Well, it's going to be once again quite straightforward. Right, what am I going to do? Well, let's just write out the good old formula f dot r hat ds. This time my r hat, of course, being what? Oops. This time, of course, my r hat. Well, let's first write f, which is pq dot r hat, and r hat is going in the positive direction this time, so it's going to be 0, 1 this time instead of 1, 0, and that's just going to give me q. Nothing big, nothing shocking, just q. And that means my final line integral, my final work done. Oh, by the way, before we do that, do you expect the work to be positive or negative? Well, let's see, what do I expect? I expect the work done to be negative, right? Because you can clearly see that the y component of these field vectors are down, whereas we're just the path of motion y component is just up. So I expect the work to be negative. So why don't we go ahead and do that, right? That's gonna be what? Just q of x comma y, I guess. Q of x comma y ds. But remember, what are we holding constant this time? We're holding x constant, folks, x. So that means I can just erase this and write x as b, right? Because we're on that part of the bounds. And let's make this negative because we intuitively thought that work should be negative, and of course this is b. So that right there is our work. The work done by the vector field at that point. Sorry, along that curve, right? And now we just have one final line integral to take, and this time the path of interest is the left hand path of motion, right? And same deal as always. This time I might actually use the bigger marker. The line integral across that surface, or that curve. I should write c is what? Of f dot r hat ds, and of course I'm going to calculate that. So f dot r hat is going to be what? Well, f is just going to be pq, and r hat is going to be what this time? Well, r hat is going to be negative this time, because take a look at the direction of motion, right? The direction of motion is just downwards. So the tangential vector, the unit tangential vector, will just be 0, minus 1, right? And what is that equal to? Well, that's just minus negative q. Now, before we go any further, let's predict what the work done will be. Well, I predict the work done will be positive, because look at the y component of these field vectors. That y component is clearly negative, and the direction of motion is also negative. So these constructively interfere, if you will, and they help each other, right? So, as a result, I can write the following. This is equal to the positive line integral is going to just be q of x comma y ds, but of course don't forget your bounds. This time x is going to be a instead of b. Why? Well, this is quite simply a. That's really all there is to it, right? So now what we're going to do is sum all of these line integrals up. So let's go ahead and add all of them up. Let's see what we get. So now hopefully you won't need that anymore. Okay, so let's go ahead and take a look at what our total work is going to be. So let me erase all of this junk. And before we proceed, let me first and foremost highlight what our answer was for the last one. It was this. Okay, so let's go ahead and take a picture of all of them, and we're going to add them up. Oh really, we don't even have to take a picture of all of them. Let's see, let's consider separately what happened. We have this, and let's paste it right there. Paste it where it belongs. And we have this, what we just got. This line integral sum. And we're adding them up. Right, we're adding these two up. So clearly something's gonna happen, right? We're gonna get what? This is gonna simplify to the integral on that curve. This is simply going to be q what? A comma y minus q b comma y ds. But hey, what does that look like? That looks to me like a derivative. Sorry, an integral. And why is that? Well, look at this. I can simply rewrite this. Let's take a look at that inside portion right here. Let's look at this inside. Right? Is that inside not equal to the integral of q from x q, which is defined as a function of x and y, from a to b, right? Sorry, from b to a. I should have switched it around. Okay. Right, does that make sense? So the integral of q of x comma y from a to b is going to be quite simply the difference of q of a comma y minus q of b comma y. And as a matter of fact, we seem to have just received a question from our live audience. Oops, and that was false hope. But let's take a look at what's going on anyway. Okay, let's try to make sense of how we can simplify this. I'm going to give the audience 10 seconds to find out. Okay, so hopefully that was enough time to meander, but now we're gonna reveal the answer. Okay, let's get another slide going if we can. So really what all of this comes down to is some basic simplification in the math and in the integration. So let's see what that simplification is, right? So as a matter of fact, it's not just q of x y, but it's much deeper than that. It's going to be partial q partial x, right? So partial q partial x, right? So not y partial x and not partial y, you may be asking, right? Well, look what's changing. It's the x component, right? That's why we're taking the differential in respect to x. And then we're going to multiply that by what? Well, by a scalar value, partial x, right? And really, this should be almost a second-hand nature to you at this point, because saying this is the same as saying what? It's the same as saying the integral of f of x is equal to f of a minus f of b. Right? So this is basically exactly the same thing. So hopefully you recognize that at first sight. Let's see if our YouTube audience has any comments, and of course not. But let's keep on going in this direction. Now that we know that, we can just plug that back in, and what are we gonna get? Well, let's see. Let's duplicate that slide. Seems like our Facebook audience has been out of the stream for quite a while, so we'll let them go at this point. Let's end that Facebook live right there. Okay, so sorry about that small disruption, but let's keep on going. Is this the duplicated slide? Oh. So now what I'm gonna do is substitute what we just got back in. Okay, so let's erase all of this. So now what I'm gonna write is quite simply the integral of on the curve C from A to B of partial q partial x partial x. Okay, that's our first part, right? But then remember, we also had that second part, right? When we were gonna subtract partial p partial y partial y. Okay, and hey, doesn't that look a lot like Green's theorem? Let's go a bit back and see what Green's theorem originally stated. We had partial q partial x minus partial p partial y. Okay, and let's go back to what we have now. We have, in essence, the same thing, right? Partial q partial y, partial x, and partial p partial y. Now, I want you to consider for a moment why that is so. Why is that true? Okay, so hopefully that was enough time. Now what we're going to do is go ahead and take the last stage of this. And the last stage is just a few simple modifications, right? Let's go ahead and erase all of this. I'm quickly approaching the limit on how many slides are allowed here, but hopefully that'll be excused by the Google faculty. Okay, and since I have two scalars right here, scalar number 1 partial x, scalar number 2 partial y, I can just go ahead and factor them out as I would normally. Right, so I can just go ahead and write as follows. Partial q partial x minus partial p partial y times partial x partial y. There you go. And last thing I want to just write down quickly is quite simply this. Right, I can just say that all of this is simply what? Well, it's just the two-dimensional curl, right? Isn't this just the equation for two-dimensional curl? Okay, and just multiply that by partial x partial y, and we're done. That is, in essence, Green Theorem. Okay, now we're gonna go ahead and try a few basic problems, just 3 problems, and let's see how we fare on that. Okay, so let's go ahead and check out the first and foremost problem. But before we go ahead and do that, let's check if our YouTube live audience has any questions. As usual, they don't. But we will continue. So let's see. What is our first question? Let's roll it up. Our first question is this. Let C be the perimeter of the rectangle with sides x equals 1, y equals 2, x equals 3, and y equals 3. Evaluate this interval. Sorry about that crazy line. Okay, first thing I'd like to do is just go ahead and write Green's theorem, if that's okay with you. Okay, so let me just take a sip. But before I finish, let's show the audience. This was the example that we just worked on. And as a matter of fact, you can visualize these kind of vector fields even online. So for example, what we just had was something like minus x, y, or x minus y, and z component 0. And for example, that vector field would look like this. And this is of course a 3-dimensional vector field, but don't worry about all of that just yet. Okay, so just wanted to show that to you folks. Anyway, back to our first problem, which is as follows. Let C be the perimeter of a rectangle with these sides and boundaries. We have to evaluate this interval. Okay, so how are we going to do this? Well, let's write down Green's theorem. What does Green's theorem tell us? I'm going to be writing on our personal device, the phone. So let's go ahead and write Green's theorem. So Green's theorem tells me as follows. Already that's too big. My line integral, right, f dot r ds over a closed path C is going to be equal to what? What is my line integral going to be equal to? Well, by Green's theorem, this is going to be equal to a double integral, right? A double integral that involves four boundaries, because we have 2 degrees of freedom, and thus 2 boundaries for each degree, giving us giving us 4 boundaries in total. Seems like our stand isn't working so fine here, but we can deal with that later. And of course, what do we have after that? We have the actual theorem, which states that partial q partial x minus partial p partial y, all of that multiplied by the scalars partial x partial y, whatever order you choose to write them down in. Okay, now all we have to do is just go ahead and do that, right? So what I can do is write partial c to partial d and partial a to partial b, and let's see what we have here. What is our p and what is our q? How do we know what our p and q is? Well, you can take a look at our it's already written in the form of line integral, so take notice of that fact and use it to find the Green Theorem version of it, right? So partial q is going to be what? First of all, we have to identify q, and q is right here. Q is the second term, really. Hopefully you can see my highlight there. Q is that second term, and maybe I'll even use the color red to indicate q. That right there is q. Okay, and this right here is going to be our p. So that's our p. Okay, now that we know what we're dealing with, let's just plug in partial q partial x. I can write as partial x of what? Well, q is just y to the 5th plus 3y squared minus 1. Okay, and I'm going to add that, subtract that, the most fundamental mistake, from partial y of p, and p of course being 3x to the 4th plus 5. I'm going to give the audience some time to go ahead and compute that, but while they're doing that, let me just put in my dx dy. Okay, let's see if we've got any comments from the live audience now. Okay, so yeah, let's go ahead and compute that. Well, it should strike you that all of this will come out to 0, right? Because we're treating y as a constant. So all of this will be 0, all of this will be 0, and we'll be left with a final answer, a final work done of 0. What does that tell us, though? What's the moral of the story? The moral of the story is that the vector field that we're working with here is conservative vector field, something like a gravitational vector field, for instance. So that's a very important key property. Okay, next problem. Let's tackle the next one. So for this problem, we have to actually evaluate the line integral. Let's go ahead and do that, right? We have our field. We have our fields, and likewise we have our region, our path, our curve. So let's go ahead and use that information to our advantage. So the first thing I want to do is actually visualize this, if that's possible. So here we are on the xy plane, and I have this crazy looking vector field. Might have vectors all over, and I'm interested in a certain region C. Okay, so I'm thinking that I can actually graph that out here. on my 3D graphing calculator. Hopefully everyone is able to see what I'm saying. Okay, audience, please let me know if the audio is broken or otherwise. So let's put in that vector field, which is what? 2y plus e to the xi. So 2y plus e to the x. That's our x component of our vector field. Our y component is x plus sine of y squared. And our z component is just 0. Wow, so that's a crazy looking vector field right there. And that's a legitimate vector field. Quite amazing. And of course I can actually zoom through the vector field right here. You can actually have some fun with these vector fields in reality. Right? But let's go back to our original goal, which was simply to find what? To find the work that this vector field does on a particle that traces out the following path. What is our path of interest? X squared plus y squared equals 1. Just the good old circle. So let's see if that actually loads right here. It says loading, but I don't know. Wow, that's amazing right there. That's amazing. So basically we have to find the work done on a particle that traces out this circular path by our vector fields. What is that? I'm not quite sure. Do we have audience member now? Okay. So yeah, that's basically our region of interest and our vector field of interest, and we have to find that. So let's go ahead and find it. Evaluate f dot ds. Well, I know that f dot ds is going to be equivalent to what? Let me write it down here because it's too hard to write it there. Have I actually disconnected? No. So let's go ahead and write that down. F dot ds is equal to the double integral over a certain region. Let's call it R just for the sake of it. And of course I'll have partial q partial x minus partial p partial y multiplied by partial x partial y. Okay, so hopefully you just saw what I wrote there. That's the Green Theorem, sorry. And now let's identify partial q partial x, right? So where is our partial q partial x, and how are we going to integrate that with our region of interest? Well, let's see how we did it for the last problem. Last problem, it was already set up for us, right? Here, however, we need to do the setting up, right? Last problem, we had the line integral set up for us. You can see that really quite clearly. Dot ds was quite simple, right? R, what was R here? So we simply had f dot r hat in this one, and f of course contained these two components, p and q. But what did r contain? Well, r contained these two components, dx dy, right? So let's try to understand that same understanding to this problem. Okay, this one might be a tad bit longer, but I think we'll be able to work through it. Okay. How can we do this one? Let me shut off that Mac. Well, in the intervening time, I encourage the audience to go ahead and try to solve this problem, and let me know in the comments below how you fare while I consider how to solve it for myself. Okay, so let's go ahead and do the following. Okay, so I just had an idea, and that idea was just to go ahead and charge through the problem, right? Here, right here, always I use the wrong color. This right here is our P, our X component. This right here is our Q, our Y component. So we have no reason why we can't compute that surface integral right here, right now. So let's do it. I'll write the following: the double integral of partial x of q, and of course I just wrote what my q was. It's x plus sine y squared. Okay, well that's a bad looking sign. And what's going to be next? Well, plus, or rather minus, partial y of the x component. And what is my x component? 2y plus e to the x. Okay. And what's the final thing I have to do? Well, I have partial x, partial y, and now let's just multiply by those scalars. Okay. Now it's just a matter of really chugging through this. So let's go through it. Partial x of that is just going to be 1. So let me actually use this marker to. So all of this is just going to condense down to 1. This is going to become what? 2. So this will just become 2. And I'm fairly sure that's it, right? And just to simplify matters, why don't we write this as dA? Okay, so I'll have 1 minus 2, which will give me minus 1, right? So do I even have any more space to write that? No. So let's duplicate this slide and go on to the next one. And Google is warning me that I can't create any more frames. Okay, so let's go ahead and just take this problem out, right? So we have partial. Let's give some credit to Leibniz for his notation, really. No less, and certainly no more. So we have 1 minus 2, that'll give me minus 1 dA, and I can take out that constant, so I'll have that. And of course this will just be equal to minus 1 times the area of whatever surface I'm considering, which in this case happens to be a circle, right? So minus pi r squared, but of course I know the radius to be 1, so I'm imagining my answer should be negative pi. So I'm going to cap it off in that, so negative pi. Okay. Did I box my previous answer for the last problem? Why don't I box it right here anyway? Okay, and our final problem is this. Use Green's theorem to find the area of a disk of radius A. Okay. How are we going to do this? To find the area of a disk of radius A. Okay, so let's write down Green's theorem. So that right there is the line integral, and of course it's equal to the double integral. Of what? Well, double integral as stated by Green's theorem of the following. Partial q partial x minus partial p partial y, and then multiply by those two infinitesimally small scalar quantities. So I want to find the area of a disk of radius A. There you go, there's my disk, radius A. Area is very closely related to mass. Right, so that's one thing that immediately pops into mind. But what is my field going to be? What's my field going to look like? Well, I'm going to ask the viewers once again to go ahead and consider solving this problem on your own before you watch me try to solve it on my own. So go ahead, try to solve the problem, and we'll be back in a few minutes. Okay, so hopefully that was enough time to go ahead and tackle the problem. Now we're going to actually solve it, right? So first and foremost, we have to parameterize our x and y variables. So let's go ahead and do that in red. So I've got my x to be a cosine theta. Hopefully you've seen that before, so it should be pretty obvious. And my y the same but with sine theta, right? So let's go ahead and calculate dx dy right off the bat. My dx is simply going to be a minus a sine theta, and my dy is going to be simply what? A cosine theta. Instead of putting that swirl, let's just do that. Okay. So I've got my parameterizations, right? What do I do next? Oh, and don't forget about the dt right here. Otherwise, that's just incomplete. Okay. Now what are we going to do? Well, at this point, it's pretty simple, because the only reason I did that is so that I could find dx dt. And now what do I know? Well, I know that dx dt is simply minus a cosine of theta. Likewise, dy dt is equal to a cosine of theta. Okay, and how does that help us? Well, alright folks, so we just received a comment from one of the viewers finally, and let's take a look and see what they're asking. Okay, so the viewer is suggesting that at this point we Okay, so our viewer has provided us a clear and straightforward way to plow through the problem. And here it is folks, right here in front of you. So we actually didn't need that dx over dt at all, right? All we needed really was as following. So let's go back to where we started. Well, we started with what? Let's start with an analog of Green's theorem, which tells us that I'll have x dy minus y dx. Then I can just plug in everything, right? X, of course, being a cosine theta, but dy being a cosine theta dt. So, wow, I'm going to need a lot of space for this. So, my x is going to be a cosine theta times a cosine theta dt times a cosine theta dt. Okay, so far so good. Minus y times dx. So my y is going to be a sine theta, and my dx is going to be minus a sine theta. Of course, all times dt. Now what does that equal? Well, that equals quite simply once again the integral of a squared cosine squared theta dt minus the minus cancels out, so plus a squared sine squared theta and times dt. Now hopefully you're seeing what I'm seeing here, because I see some great stuff. Great opportunity right here. So I'll have let's factor out that a squared, so that I'll just get that simple trigonometric function right there. So if we can just factor out that a squared, and of course this becomes 1 dt. That tells me that this will become a squared t. But are we done, folks? Are we done? No, because remember, this should be a definite interval from 0 to 2 pi, right? So let me put those bounds in. So from 0 to 2 pi, okay? And really that changes a bit. So that means my t will go from 0 to 2 pi, telling me that at the end of the day, I'll be left with none other than 2 pi a squared, right? But of course we take half of that for symmetry, and we're left with pi a squared, which is indeed the area of any circle. So folks, thank you for watching my deep dive into Green's theorem. We've collectively taken a look at line integrals. We've seen their connection with mass and work. We've seen how we can use those analogies of mass and work to tie in the line integral with the Green theorem, right? Through mass, we can connect them, but through work, we've really seen how to prove the Green theorem. And lastly, we took a look at 3 problems that utilize Green theorem. Okay, so thank you for learning with me today. I enjoyed learning with you.